Okay, hi, welcome back to, we keep calling it drunk physics, but this is going to be a little subsection of the one that I just did. So I want to talk about the metric tensor, because we talked about tensors and things like that, but I want to actually kind of give a little bit of intuition as to what kind of objects these mathematical things are and what kind of power they have. So, I mean, you can read this for yourself, but we have an array of values right here. Normally this would be contained in brackets, but it was kind of hard to I don't know, I just kind of threw this together. So you'll notice that each of these values here, these MTT, MTX, MTY, well, they're all arranged in such a way that it all equals this one matrix. So you can generalize any matrix, especially in this particular type of tensor, the 3+1 space-time tensor. I think this is contravariant because these are on bottom. I don't remember if contravariant or covariant is on bottom, but there are two types of tensors, and they're kind of how you talk about them in like relationship to themselves or in relationships to other tensors. I'm still kind of getting my way through that idea and what that actually means, but so you can think about tensors as each one of these columns here, a single column going straight up and down. Well, let's get out a pencil and kind of mark on it. So a single column can be thought of as one single vector, okay? And then you would multiply it by the components of a vector. Wait, I think I did that wrong. No, there's matrix mathematics here, and I don't need to get into it because, you know, there's a lot going on. But you have these components, and they're all time. They're all dependent on time in one sense, or you can also have a vector going this way, and then they're all how it acts on time, I guess you would say. I think the second. Well, either way, the way you think about it is like, let's take our cube here. We have a nice, cute little cube. This isn't exactly kind of what I wrote, but you have 3 dimensions here. And in the other case over on this side here, you have that 4-dimensional thing. But let's think about it as acting on faces of a cube. That's the first intuition to build. Notice that you have this value here. This is in your x direction. You're going over to this side of the screen. So we're going this way, all right? Arrows are cool. So that is your XX value. That's the force pulling this side of the cube this way. So this side of the cube all the way over here, and then you have them all the way on the other side. You know, and I think they would take on your negative value. So if you go back this way, you pull on this side, then it's a negative value of this, but it's still the same like signature here, kind of, in a way of thinking. I mean, you have to think about this little block here as like the tiniest block you could ever make, and the force is acting on the tiniest, faces of the tiniest block in the world, all right? That's a certain way of thinking about it. And then you have all these other forces that act in the same direction. You got one coming down this way, so it's stretching this side of the face, so it kind of comes out a little bit more. That's what that motion would do. It would tend to stretch this face, so it's a little bit longer. You see how that works? And this would tend to stretch this face so that, let's see, how do I draw that in perspective? Kind of think about it as stretching this face out a little bit more. You're bulging it out, all right? Pretty simple. And then you do that with all of them. You have your y direction here, and then you have your z direction going, which way is it? You have their orientations. Yeah, so your z direction is pulling out your z face. All right, and then you have all of the other squishing and morphing. So that's kind of what this object is it forms the basis vectors in a certain way. In a way of thinking, it forms kind of what, when you take a step in a certain direction, like, where do you end up when you take exactly one step in that direction? Do you end up 2 units over here, or do you end up 1 unit when you go this way? Okay, so pretty simple ideas, but how does it really? Well, obviously you can work on this. Okay, you can make this less general. So then we come down to the metric tensor itself, and when you want to talk about a metric tensor, then you have this one thing here, and each one of these vectors is going to get acted on, and that forms like, okay, when I go straight out into time, how many units of time do I go, with each infinitesimal step, kind of. It's a line element. So then you can think about it as, the force pulling a cube's x face in the x direction, and then this is like only in time. So now you have to add time to it, and then this gets kind of hard to talk about because tensors are really complicated things, but I'm trying to explain them as simply as I know how to explain them. So you get this line element here. This equation says, okay, so if I'm going a differential step in time, then each differential step in time is going to, in a certain sense, be g sub tt units. So it's going to pull me in time, with a constant or, along some function, so I could be writing a sine wave through time, that's like, I go back and forth in time, basically, if it's a sine. That doesn't really make any sense, but it's a thing to think about. It's a thing you can do. I could replace GTT with sine of, I don't know, t I want to go with. So then as each t ticks on, each tick of time happens, you start going one way and then you start going back the other way. And then, it's like a periodic pendulum swinging kind of thing. And you can do that with any direction. You can really add anything you want to this. But then we talk about the first idea of flat space-time. So now we take this GTT, but we call it negative. Now that's just a convention thing. There's really... it doesn't really make much sense why that is without really getting in depth into this kind of idea. But then your other three here, let's grab my pen again. I'll write on this. So this little vector this matrix within a matrix, yeah, inception, right? So this whole matrix is one thing. But then you add a row and a column, and then those are your time-dependent variables and so forth. But these are your space-only variables, these guys. So then we can write space only. So this only talks about things that happen in space. So why don't we include these guys here, these, get my pen out again. Why don't we include these zeros? Why are these 0? Well, it's because we want to talk about, whatever. Hold on a sec. Okay, so we're going to go back. That was weird for a second. Things happen kind of when you're running a live stream off of your computer's desktop. So back to here, why don't we use these? Well, these are shear forces. So this is going to be, if you have your cube, your nice little cube, it's going to tend to want to distort it this way. Those are your shear forces pushing it in like kind of opposite directions. Like, so you make it, it's tending to turn a rectangle into a parallelogram, basically, is those shear forces. So these would be shear stress. And of course, we remember that stress is invariant in time. It just is. It's there. It's a force that's there. And, it's just there. It's pressing. It's pressing constantly in time at the same pressure. And then you have... these are these 1, 1, 1s here. That's like one step this way is equal to one step this way. So it's really just an identity matrix in a certain sense. And then that describes flat space-time. So what I did here is you take these line elements from ds squared equals gtt gxx dr, and then you replace these numbers here, this variable gtt with -1, all right, and then it activates that line element. Basically, it's like turning a switch on for it. Oh, and I forgot to delete these. So then you can effectively delete these because it is one GYY unit, which is like a movement in that direction. If I can get this thing to actually do what I want to. That's going to have to do for now. And we can get rid of that. And then boom, now you have, or you can even take it a step further and you can get rid of the ones altogether. Yeah. You just take the ones out. Boom. Alright, and then now it's dy. Oops, no, let's just take the ones out. And then there you go. That's your line element for your metric. Now, what does this mean? Well, you have to think about the distance formula. It's like the distance formula in space, and it gives you how to compute your distance formula. So think about it like, what is it? Pythagorean formula, where what is it? A squared equals b squared plus c squared. So kind of that thing. And then you take your square roots of it. You take the square root of this, and then each of these squared is going to it's going to make your distance. It's going to show you how you have a distance formula for that metric, and really that's the whole point of a metric. I mean, there's not really much more to explain about what a metric is, except to show you new examples of metrics, and we already showed you one example, a Schwarzschild metric. So cool. And of course, like and subscribe. Yeah, do that, and also stay away from sharp objects. All right, and that's that. Thank you. Take care and have a great day.